Partial derivatives. A partial derivative is a derivative where we hold some variables constant, like in this example. When we find the slope in the y direction while keeping x fixed, we have found a partial derivative. Or we can find the slope in the x direction while keeping y fixed. Let's first think about a function of one variable, x. Fx is equals x elevated to the second power. We can find its derivative using the power rule. The derivative of x is equals to x, but what about a function of two variables, like x and y? Fxy equals x elevated to the second power plus y elevated to the third power. We can find its partial derivative with respect to x when we treat y as a constant. Imagine y is number 7 or something. The derivative of x is equals to x plus 0 equals to x. Explanation. The derivative of x elevated to the second power with respect to x is 2x. We treat y as a constant. So, y elevated to the third power is also a constant. Imagine y equals 7. Then 7 elevated to the third power is equals 43 is also a constant. And the derivative of a constant is 0. To find the partial derivative with respect to y, we treat x as a constant. The derivative of y is equals 0 plus 3, who multiply y elevated to the second power is equals 3, who multiply y elevated to the second power. Explanation. We now treat x as a constant, so x elevated to the second power is also a constant, and the derivative of a constant is 0. The derivative of x elevated to the third power with respect to y is 3, who multiply y elevated to the second power. That is all there is to it. Just remember to try all other variables as if they are constant. Now, let's talk about tangent planes. Tangent plane to determine the equation of the tangent plane to the graph of z equals f x y. Let p equals a b f a b be a point on the surface above a b in the xy plane as shown to the right below, sealing to the surface with vertical plane y equals b and x equals a. Creates two curves on this graph, both facing tone p. These two space curves are the graphs of vector functions. R1 x equals the vector x b f x b. R2 y equals the vector a y f I y. Showing the orange on the surface the vector derivatives. T1 equals the derivative of R1a equals I plus f a b k. T2 equals the derivative of R2b equals j plus fy a b k. Are tangent vectors at p of the graph of f, while the plane contains p as well as T1 and T2 is the tangent plane of p. To calculate the equation of the tangent plane at b, a, b, c, we need its normal. On the other hand, if key x, y, and z is an arbitrary point in the tangent plane as p, a, b, c, then pq vector equals the vector x minus a, y minus b, and z minus fib. Lies in its plane and so it's perpendicular to n. Thus its point normal for the equation of the tangent plane is vector x minus a, y minus b, c minus a, b, who multiply n equals the vector x minus I, y minus b, c minus fib, plus the vector fxib minus fyib and 1 is equals minus x minus a fxib minus y minus b fyib plus c minus fib equals 0. So the equation of the tangent plane at ABFIB is C equals FIB plus x minus I fxib plus y minus b fyb a. And these are some examples.
Implicit derivation. The implicit derivation uses when a function is not arbitrary. For example, x squared 2 plus j squared 2 equals 1, x squared 2 and plus j squared 2 equals 1. The causes we cannot differentiate directly is why the normal function in nests. We uses the implicit differentiation, which consists of differentiating both uses of the equation with respect to x and train j is a function to x, and applying the chain rule when differentiating terms with j. Implicit differentiating is a technique in calculus uses the derivative of a function that is not explicit in terms of a single variable. That is when equation involves two or more variables, example x and j, mixes in a single expression and is not easy to solve from j is a function of x. Implicit differentiating is uses the orbit and dj and dx.
Hello everyone, I'm going to show you how to find the equation of the tangent plane to a surface given by a function of two variables. We are given the surface C equals the square root of x times cosine of t. And the point is b over 3, 0, and the square b root of b over 3. This point lies on the surface because when we play in xb over 3 and g0, we get c equals the square root of b over 3 times cosine of 0. Which is 1. So C equals the square root of b over 3. To find the tangent plane, we net the partial derivatives of c with respect to x and g. Let's compute. The partial derivative of c with respect to x equals 1 over 2 times the square root of times cosine g times cosine g. The partial derivative of c respect x to equals 1 over 2 times the square root of x times cosine g times cosine g. So the partial derivative theta c respect to g equals 1 over 2 times the square root of x times cosine g times cosine g. So the partial derivative of c with respect to g equals 1 over 2 times the square root of x times cosine g times cosine g. Point x p over 3 and g equals 0. It becomes 1 over 2 times the square p over 3. So it becomes 1 over 2 times the square root of p over 3. So one over 2 times the square root of p over 3. So p over negative 3 0 equals 0. So the general formula for the tangent plane at a point x, g, and c is c equals now plus the partial derivative of c with respect to x times the quantity x minus x now plus the partial derivative of c with respect to g times the quantity g minus g now. So c equals c now plus the partial derivative of c with respect to x times the quantity x minus x now plus the partial derivative of c with respect to times the quantity g minus now. Substitute every time. C equals the square root of p over 3 plus 1 over 2 times the square root of p over 3 times the quantity x minus p over 3. So c equals the square root of p over 3 plus 1 over 2 times the square root of p over 3 times the quantity x minus p over 3. And finally,
hello, my name is Leonel, and to clarify this, I am going to do an exercise. We have our equation of the tangent plane. I am writing it down because we will use it to substitute our values. We have our equation. And our points. To begin, we derive our equation with respect to x. And now do the same but with respect to y. The next step is to substitute two values of the point into our x equation and into our y equation. Now we solve the two equations on the calculator. With respect x 36. With respect to y is 120. Finally, to finish, we substitute our values in the tangent plane equation. We solve what we have in the parentheses. Now we reduce. And to finish, we use solve. We are done. These are our results.